morning, everyone. Thank you for coming to this tech seminar today. We have a special guest, Dr. Dominic Miser from the TechX Corporation. He's a research scientist, has some pretty interesting things to share with us. One thing I do need to reiterate is that this is unclassified, so please keep the conversations at that level. And I will just do a brief intro. The abstract says, optical atomic clocks are rapidly becoming the most stable clocks, surpassing C's and other microwave standards by more than an order of magnitude in total clock stability. The next generation of optical atomic clock promises to surpass a stability level of 1 part in 10 to the 18th, enabling intriguing new applications for optical atomic clocks. If you don't already have the abstract, you're welcome to grab it outside when you leave. Please help me welcome Dr. Miser.
Thanks for the introduction. I'm absolutely delighted that so many of you showed up to hear my talk. What I'd like to do today is I'd like to give you a little bit of an overview of what's been happening in the field of ultra-cold atomic clocks over the last 10 years or so. And I would like to discuss some of the really amazing applications that are enabled by these new levels of performance that are being achieved today. And I'll discuss one of the main technical challenges that we are facing in taking this technology out of the lab and putting it into the real world, and in particular, putting it into space. And I'll talk about one approach that we've come up with to deal with that challenge. Before I get into the more technical details, I'd like to give you a little bit of a background about myself and the company that I work for. My background is in ultra-cold atomic physics, laser physics, quantum optics. And about 3 years ago, I decided to take a little bit of a break from that, and I joined TechX, which is a company that does scientific computation, high-performance computing, mostly in the areas of plasma physics. So we're about 45 scientists and software people. About 2/3 of us have PhDs in physics. We are located in Boulder, Colorado. And like I said, we do a lot of large-scale physics simulations and performance improvement consulting, big data, distribution management, and visualization. And we collaborate with lots of partners in industry, academia, as well as in DoD. And one of the really cool things about living and working in Boulder is that you get to interact with some of the key players in the field of atomic clocks. So this includes my postdoc supervisor, Murray Holland, but also other people like Jun Yi, who's built some of the most stable clocks to date, John Bollinger and Dave Vineland, who won the Nobel Prize in Physics last year, Andrew Ludlow, and James Thompson. So I think the reason why I'm here is this chart here. Atomic clocks, so maybe even more generally, time is the quantity that we know how to measure the best by far, by many orders of magnitude. That's been so for many centuries, really. And it's been especially true during the last 7 decades or so, where microwave-based atomic frequency standards have improved approximately exponentially, starting at an instability of about 1 part in 10 to the 11, and today reaching stability levels of about 1 part in 10 to the 16. And so this has been going on for 7 decades, and then over the last 2 decades, a new technology has entered the stage and is making even faster progress. And those are atomic clocks based on optical atomic transitions. And so these have started out at about the same level as the microwave clocks, but on the log scale, it looks like maybe they're improving exponentially, but if you were to look at it not on a log scale, it just looks like they're crashing down to basically this level of 1 part in 10 to the 18 that they're reaching today. And they're now more stable than microwave clocks. Okay, that's all nice and good. But what can you do with that? When I tell my mom that I work on optical atomic clocks, she asks me, well, that's stupid. Who wants to know a second to an accuracy of 1 part in 10 to the 18? Well, the answer is there's a lot of really cool things that you can do if you have that level of performance. And a lot of these applications work even better if you have an atomic clock in space. The really obvious one is navigation, GPS. Today's GPS is based on microwave clocks, and if we were to improve the performance of these clocks, that would directly translate into improved performance of GPS. Other applications are synchronization across large distributed computer networks, and then something that is just absurd in my mind, the fact that you can do geodesy using these clocks. Geodesy means you measure properties of the Earth, such as the equipotential surface of the gravitational potential. And these latest generations of clocks reach a level of performance where you can measure height differences on the order of a centimeter. And that opens up a lot of really new applications that we weren't really able to think about maybe even 10 years ago. Other applications include communication. So there are some fiber communication, optical fiber communication networks now that are fully coherent. And in order to operate those, you need synchronization across large distances. And that is impossible to do if you don't have an absolute frequency reference. Other things are more traditional clock applications, distribution of timing and frequency information, for example, through the NSA Global Distributed Time and Frequency Architecture. And then another thing that I find really intriguing is the possibility to build networks of clocks that communicate with each other through quantum communication protocols. And I'll get into some of these applications in more detail on the following slides. So I mentioned this fact that we can now measure height differences just using clocks. So there's this general relativistic effect where clocks move faster if they are higher in the gravitational potential. And this data here is from an experiment that was performed in 2011 in the lab of David Vineland. And what they did is they took a clock, they let the clock run, they measured time with it, and then they lift the clock. They had this entire optical table on jacks, and they lifted it by about a foot, and then they measured time again. And just like general relativity predicts, that clock goes faster. And the precision of these clocks was such that they were able to measure this height difference in about 3 hours of averaging time for each one of these data points. Now this is 2011, and this is using a slightly different clock architecture than what I'm talking about today. If you were to repeat this experiment with today's most stable clocks, you'd be able to obtain each one of these data points in a second. Alternatively, if you were willing to measure for an hour or 3 hours, the error bars on each one of these would be a factor 10 to 100 smaller. And so you could easily imagine how you'd be able to measure height differences on the order of a centimeter with that. So, like I said, you can measure the location of the geoid to within a centimeter. The geoid is the equipotential surface of the gravitational potential. And what that allows you to do is it allows you to tomographically reconstruct gravitational perturbations. That is not possible if you don't have a measurement of the gravitational potential. If you're just able to measure gravitational force, little g, not the big G, you only get information about some source mass and divided by the distance from that source squared. So you're not able to disentangle whether this force is due to a large mass or a close distance. If you're, on the other hand, able to measure both of these simultaneously, you can resolve that ambiguity and you can find out whether a certain gravitational perturbation is due to groundwater, stuff like oil and gas reservoirs, minerals, metals, or even smaller structures, maybe caves or man-made structures like bunkers. And one of the things that is really intriguing about this approach is there's no such thing as anti-mass. So you can't shield gravitational perturbation by putting some other stuff around it. Okay. Quantum networks of clocks. What is the idea here? So the idea is you have several satellites orbiting around the Earth. Each one of them has an optical atomic clock on it. And you quantum mechanically entangle these different clocks with each other through a certain quantum cryptographic protocol. So basically what you do is you have the atoms that constitute your clock on one of the satellites. You create a GHZ state. You entangle two of these atoms with each other, and you teleport that pair to a different clock. The end result is that all atoms, both on your local clock on one of those satellites, as well as the remote clock on some other satellite, are in some globally entangled state. And that allows you to do, that has several advantages. First of all, you're able to optimally use all resources that you have on these satellites. So your overall instability scales like 1 over root number of the total number of atoms in this clock ensemble, rather than just the n for each satellite. This clock is also robust against failures in the clock network. A common problem in timing distribution is what happens if one of your clocks goes bad and goes either much too fast or much too slow. How do you detect that? This system is automatically, through this quantum entanglement process, robust against that. It's also robust against somebody else trying to tamper with one of your clocks, artificially making it too fast or too slow. And you'll be able to detect if somebody else is trying to tap into your timing signal. So you're robust against eavesdropping. And none of this is possible with microwave clocks, simply because we do not have detectors that can detect microwave photons at a single photon level. You can only do this with optical clocks. And just to illustrate that this is not anything new, other people are interested in this as well. The European Space Agency has been working towards putting optical atomic clocks in space for a while. There's been 4 workshops now on optical atomic clocks in space over the last few years. They have this STE Quest mission, which is a science mission to do general relativity experiments using clocks. And they have the SOC, Space Optical Clock Project, where the goal is to put an optical atomic clock on the International Space Station. And that picture on the right here shows the atom source and the chamber in which they keep the atoms for the clock that they developed to try and put into space. So there's an oven here that evaporates atoms, a Siemens slower, and then a Mott chamber. And yeah. And so yeah, they're hoping to get an optical atomic clock into space, maybe in mid-2020s. They think that they're pretty much done with laboratory prototypes of both ion and lattice clocks. And they've started to space qualify several of the key components. So how does an optical atomic clock work? There are 3 main components that make up an optical atomic clock. The most important one is an atomic system that has a narrow resonance that is not very sensitive to environmental effects. So you take some atomic species that has two so-called clock states, ground state E1 and an excited state, and a very well-defined transition frequency. And what you do is you take a laser, you do spectroscopy to measure that resonance feature, and through feedback you lock that laser to the atomic resonance. At this point you have a laser that oscillates exactly at this frequency h nu 0. And then you take that laser and you stick it into something called an optical frequency comb, and that allows you to translate that optical frequency into the frequency range that you're interested in. Most of the time these will be electronic frequencies somewhere in the gigahertz range. And I'll spend the next few slides to talk about these three components in more detail. First, the atoms. Like I said, you typically take atoms with a very narrow line width. And the way to get to these narrow line widths is you take a group 2 atom. Group 2 atoms have 2 valence electrons, and just like helium, they have 2 very different kinds of states. They have states where the spins of the electrons are anti-aligned with each other. Those are called singlet states. And they have states where the electrons are parallel. The spins of the electrons are parallel to each other. Those are the triplet states. And transitions between these different groups of states are very weak because they are forbidden by symmetries. And so this is a popular transition. It's used in strontium. It's the transition between the ground state and the lowest excited state in the triplet manifold. And these excited states have lifetimes on the order of hundreds of seconds. So this is much longer than what you would have for a dipole allowed transition. In a normal dipole allowed transition, this lifetime would be maybe 10 nanoseconds. So it's a huge difference. So you take these atoms, you stick them into a vacuum chamber, you laser cool them to about microkelvin temperatures, and then you put them into a trap. You put them into a trap so you can interrogate them for as long as possible. And one of the advantages of clocks with neutral atoms versus clocks with ions is that you can pack a large number of neutral atoms into that trap, and that allows you to get better signal-to-noise ratio. In the rest of this talk, I'll almost exclusively be talking about these clocks, neutral atom clocks, because I think in the future they'll achieve the best performance. The next component is this laser that you need to do the spectroscopy, to do the interrogation of the atomic line. Now that's a pretty crazy laser. The best lasers used for this purpose today have line widths that are fractions of a hertz. So that corresponds to a Q factor of that oscillator on the order of 10 to the 15. So the light coming out of this laser undergoes 10 to the 15 oscillations before it loses coherence. And how do you make such a laser? It's conceptually simple, but actually doing it is very hard. Conceptually, what you do is you take pretty much a standard diode laser, not too different from what's in this laser pointer, and you electronically stabilize its frequency against a reference cavity, one of these beasties here. And it's really the construction of these reference cavities that's the big challenge. Everything else is, comparatively speaking, easy. The electronics is well understood. The diode laser itself is well understood. It's really making this reference cavity that's hard. And why is it hard? It is hard because the limiting factor are the thermal vibrations in the coatings of these end mirrors in the cavity. And there's not really a whole lot that you can do to get rid of those thermal fluctuations. And to give you an idea of the level of performance that we're talking about, the fluctuations of these mirror substrates amounts to something like 10 to the minus 18 meters. That is a ridiculously small distance. If you compare that with the typical size of an atom, which is 10 to the minus 10, this is 100 million times smaller. And it's even 1,000 times smaller than a nucleus. So to get the best performance, you really have to work very, very hard to build these reference cavities. The next component, and this is really what's enabled optical atomic clocks to become useful. People were able to do the spectroscopy part for several decades before they were able to use it for clock purposes. That's the optical frequency cone. I'll not go into too much detail here because for the purposes of building clocks, it's largely a solved problem. But just to give you a quick idea, up here is a picture of one of these beasties. And basically what it is it's a phase-locked titanium sapphire laser that has a very broad spectrum, a spectrum that spans a whole octave. And you can see a picture that it took of that spectrum in the back of that photo up there. And what that allows you to do is it allows you to pick up two frequency components that are separated from each other by a whole octave, and that allows you to translate the optical frequencies in that laser to two microwave frequencies, namely the offset of this whole frequency cone. You can shift it left and right. That's this F sub O, as well as the repetition rate of the laser, F rep. And the cool thing is that these two microwave frequencies are linked to the optical frequency just through an integer that has no noise on it. And that allows you to translate the optical frequency without really any noise into F rep and F offset. Conceptually, the way you can think about this is it's like a gear. You have the optical frequency that spins really, really fast there, but it drives this very big wheel much more slowly. And that then is translated into some microwave output. So to the extent that none of these teeth are slipping against each other, you exactly translate that high frequency to a low frequency. Like I said, building these reference cavities is one of the biggest challenges in constructing high-performance clocks. And the way that you can tell that this is really one of the limiting factors for clock performance is whenever somebody builds a new reference cavity, for sure, within half a year, there's going to be a big paper in Nature or Science where somebody's built a clock that's about a factor 10 better. And so basically, these cavities are football sized, roughly. They're typically made out of silica. This guy over here is currently the best one that we have, and it's made out of a single crystal of silica. So basically, you take one of those big single crystals that the computer chip industry uses to manufacture their chips, and you machine out of that the spacers for this reference cavity. So once you've got it done, once you've got it built, you have to very carefully vibration isolate it, and you have to do temperature stabilization. And it's pretty clear that a lot of these challenges are not going to get any easier once you try and put one of these things into space. So we thought, wouldn't it be nice if we could get rid of these reference cavities altogether? Just cut out all those problems. And that's what this paper of ours was about 5 years ago. And this is awful. I'm just bragging. But I'm obviously very proud of this paper. There's been dozens of papers based directly on this work since it's been written. And to this paper itself, there have been about 100 citations, and to this field, there have been thousands of citations. So this is just to illustrate that this is a real, an actual thing, and not just a weird idea. And in fact, what I'm most proud of is that most of the papers have been written by experimentalists. So what was that idea? How could we possibly get rid of the reference cavities? First, very naive idea that we had is, what would happen if we were to use the atoms that we use for the clock to build a laser? So we start out with this very narrow clock transition, and we use that as our laser transition. So how does a laser work? You have a cavity that's composed of two mirrors, more or less. You have a gain medium, and you somehow need to be able to stick energy into that gain medium, and out comes light. And so our naive idea was, shouldn't the light that comes out here be very stable just because we use this very narrow transition? And as we'll see, the answer is yes. And the light that comes out is in fact more stable than what you can do with a reference cavity without having all of the problems of a reference cavity. But there are many key questions that you have to answer. First of all, if you make a back of the envelope calculation, you find out that a light source like this has typically less than one photon in the cavity. Well, that seems weird, right? Because the S and the E in laser stand for stimulated emission. How can you have stimulated emission if there's no photons there to stimulate the emission? And then for practical purposes, you have to ask yourself, do I get enough light out of this light source to do anything useful with it? So let me try and answer those questions. But first off, it's clear from the start that this is a very exotic light source. It's qualitatively different from existing lasers. Almost all lasers that we use today are in what's called the good cavity limit. In the good cavity limit, the line width of the cavity, this kappa here, is much smaller than the line width of the atomic gain medium. And as a result, you end up with lots of photons bouncing around in your cavity, and your atomic medium is relatively disorganized and incoherent. The atoms adiabatically track what the field is doing, and almost all of your coherence is stored in the light field, not in the atoms. That is completely reversed for the light source that we're talking about here. In our case, the atomic line width is much more narrow than the cavity line width, just because we're using these very narrow line width atoms. And as a consequence, you have very, very little light bouncing around in your oscillator. And in fact, so little light that it's not able to store coherence. Instead, the coherence of this light source is stored in the atomic medium. And this chart down here shows some of the typical laser systems, some of the laser systems considered so far, and how far they penetrate into this bad cavity limit. This was an experimental paper, and they simulated our light source using rubidium on something that's not really a clock transition. And so they were already about 3 orders of magnitude into this new regime of extremely bad cavity lasers. If you were to build this light source with a true optical clock transition, you would end up even further into this bad cavity limit. So really, when we started to work on this, we had to do a lot of basic laser physics. We had to revisit a lot of our intuitive understanding of lasers to determine if this light source made sense and if it could work. First, the reason why we looked into this in the first place was to come up with a stable light source. So to determine how stable the light is, we calculated the line width. And I'm showing that down here, and I'll walk you through this plot in a minute. So what's on the horizontal axis is the rate at which you pump energy into the atomic gain medium. So you can think of this as the power that you stick into the system. On the vertical axis is the number of atoms. So here 10,000 atoms, a million atoms. And let me start by taking a slice through this plot along this line of 10 to the 6 atoms up there. What you see is that there are several different regimes that you go through. Down here, if you stick very little power into your laser, you're below threshold, and you get no light out, and you have no coherence. And so your line width is relatively large. In fact, it's much larger than the natural line width of the atoms. Once your power exceeds the natural line width of the atoms, your line width drops very rapidly. That's where you undergo a phase transition. This corresponds to threshold in a normal laser. And your line width, in fact, keeps dropping until your power exceeds the so-called inhomogeneously broadened line width. Then it stays relatively constant, and then eventually you'll see something that you don't normally see in a laser, which is your line width goes up again very rapidly. So it's as if you had a second threshold in this light source where you just drive the laser so hard that you don't get any light out anymore. You'll get to that in more detail when I'll talk about intensities. So if we were to put this into actual numbers, you'll find that the Q, so the quality factor of this light source, will be on the order of about 10 to the 18 using very conservative estimates for what's pretty much doable with atomic clock technology today. And the fundamental limits are much lower than that. The fundamental limit on the line width is a parameter C called the cooperativity parameter of cavity QED times the natural line width of the atoms. The weird and cool thing about this formula is that normally you have to work hard to make this C large. It's difficult to make it large. It's easy to make it small. So by doing a bad job, by making this C small, you end up with a more narrow line width. Of course, there's a price you have to pay for that, and I'll get to that on the next slide. But just to underline one more time that this is qualitatively different from a normal laser, this limit up here is much lower than the Charlotte-Towns limit, which is the normal fundamental limit on the line width for a laser. Intensity. How much power can we get out of this laser? I'm showing a similar plot down here. So here is the amount of power that you stick into the atomic gain medium. Here's the number of atoms, and color-coded is the intensity that you get out. So you can see you go through this first threshold at gamma, and the power that you get out starts increasing. And when you get to that second threshold, W max, your power drops very abruptly to almost zero. And the cool and encouraging thing about this is that the area where you get the most power overlaps with the area where you get the narrowest line width. So you can have both narrow line width and a lot of power. A lot of power is in quotation marks here, because we're talking about a picowatt up there. It sounds like it's not a whole lot, but in the context of clocks, where you can interact coherently with that radiation for a very long time, that is actually a fair amount. So for example, when people did a coherent frequency link from the Physikalisch-Technische Bundesanstalt in Germany to the Max Planck Institute for Quantum Optics in Munich, they had about maybe 300 or 400 miles of fiber, and the attenuation in the fiber is such that at each one of these little repeaters, you end up with only about 10 femtowatt. So we know that a picowatt is plenty good enough for the applications that we have in mind here. The other thing is, if you look at just the formula for the maximum power that you can get out, it's actually quite intuitive. So this is the energy that you get out per photon that's emitted by these atoms. Each atom emits roughly at c times gamma, and there's n of them. But I'm not having just a factor n here. I have factor n squared. Why is that square there? The square is there because this is a collective effect. The radiation emitted by all the atoms interferes constructively to give you this n squared. So amplitudes go like n, and this power goes like n squared. And this formula also tells you why you might not want to crank the C down too much. You might not want to get too greedy with your line width, because as you decrease C, your power goes down. But you have two knobs to turn, and that's, that gives you a lot of wiggle room. So you can play with N to give you large power, and once you have fixed your N, you cranked it up as much as you can. That's when you start playing with your C, and you turn that down as far as you want to get the best line width. So that line width calculation was done on paper. It was basically done assuming that your laser cavity is perfectly stable. And that is, of course, a fraud. In reality, the mirrors of that cavity will fluctuate just like the mirrors of the reference cavity. So what you have to ask yourself is, what happens to the light that comes out of this light source when I have mirror vibrations? And so we looked into that, and you find that there is a built-in suppression mechanism of the frequency response of that laser to fluctuations of the cavity mirrors. It's intuitively clear that this has to happen because the atoms essentially sit in the dark. There's so little light oscillating in this cavity that the atoms just cannot sense what the mirrors are doing. They don't care. This cavity could be shaking like crazy. The atoms don't care. There's no photon to tell them what's going on with the mirrors. This is in stark contrast to what you have in a normal laser, where your atoms are clued into what the cavity is doing at all times because you have a huge number of photons bouncing around. And this is not just a cute picture or just a theoretical idea. This has been demonstrated in experiment. So James Thomson has done this experiment with rubidium, and they found for their setup that there was a suppression of about 4 orders of magnitude relative to how much vibration do I stick into the cavity mirrors versus what is the frequency response of the light that comes out. And theoretically, the suppression could be much larger, and it will be so if you were to build this light source with actual clock transition atoms and not rubidium. So at this point, we feel that the basic working principles of this light source are well understood. We understand its line width, we understand the collective emission process that gives rise to this laser. It's not a normal laser. And we understand that cavity noise does not really show up in the laser noise. And we think that now it's time to take this technology and move it out of the lab and into the real world. And when you want to do that, you have to have simulation. So far, almost all of these calculations have been carried out using very reduced, almost toy models. We carefully estimated the various dirt effects that we don't want to worry about to make sure that our calculations make sense. But in the end of the day, these are all mostly qualitative calculations. They don't have detailed, quantitative, predictive power. In order to do that, you have to do simulations to take all of these nasty real-world effects into account. And the main reason why you have to do that is if you want to optimize your design, it's going to be extremely time-consuming if you have to do it in experiment, because most of the parameters that we're trying to optimize are of a discrete nature. So it's not like, okay, I'm going to tweak the power here or I'm going to tweak the frequency here. It's questions like, what atom should I use? And when I want to change the atomic species in one of these experiments, it takes you at least a year to do that. It's extremely time-consuming. Or I want to change my cavity geometry. Ripping apart your vacuum chamber, putting in a new cavity, all of that stuff takes at least half a year, maybe a year. Other things like, what laser geometry should I be using to stick energy into this medium? If you have to buy new lasers, install new lasers, tune everything, get everything up and running and stable, it takes a really long time. So the bottom line is, you don't want to just be exploring this huge parameter space by switching up parameters in experiment. You need a design tool that helps you with that. So one of the things that you need to do a better job at is dealing with the internal dynamics of the atoms. Almost all of the results that I've presented so far were obtained using this extremely simple model where you have just two internal atomic quantum states, a ground state and an excited state, with maybe two parameters, transition frequency and a dipole matrix element for that transition. Well, reality looks like this. You have maybe 100 states, and you have tens of fields, tens of lasers coupling these different fields, and all the levels responding differently to external fields. So when you get to the stage where you want to do engineering, and you want to find out what is the best power, for example, to do my interrogation, what's the best power to do my pumping, etc., etc., you have to have a quantitative and detailed model for this internal dynamics. And there are many other things that you need to look at. One of the things that's been largely neglected so far is the effect of spatial inhomogeneities. So your laser cavity field really is typically a sinusoidally varying mode, and it's got a transverse Gaussian, and all of that spatial structure has not been taken into account in detail so far. Other things are the lasers that you use to do your pumping may not overlap with the entire cloud. And there are spatial variations in the pumping laser. And what role does that play for the performance of your laser? Other things that you want to explore are an inherent problem with all of these neutral atomic clocks is that you have to deal with atom loss. So basically the way this works is you collect atoms out of a background vapor, you cool them, and you stick them into a trap. But they don't live indefinitely in that trap. They only live about for a second. So every second, you have to reload atoms into that trap. Well, there's a basic problem here. We are shooting for a laser stability of 1 millihertz. That requires you to operate for at least 1,000 seconds. How are you going to do that if you lose your atoms every second? Well, it turns out there are several solutions to that. For example, you could just have a beam of atoms crossing your cavity. You could build something like a beam laser. Or you could have what's called a conveyor belt that moves atoms into the cavity volume, lets them interact with the cavity, Then you move them back out to repump them, and you move them back in, etc. So the bottom line is there are a lot of detailed questions that you want to answer, and we're currently not able to do that on the theory side. So with that, I'll wrap up. I think that optical atomic clocks in space offer really unique opportunities. And we have proposed a light source that is capable of boosting the performance of existing optical atomic clocks by about 2 orders of magnitude. And we think that at this point, the basic principles of this clock are pretty well understood, and it's time now to engage in detailed quantitative simulations to provide a design tool to optimize and build this clock for the real world. Thanks.